Hello everybody, let's start today's lecture. Today we will talk about text classification. Given a text, either a single sentence or multiple sentences, we like to assign a class for that text, and to do this we are gonna use this technique, machine learning technique, naive Bayes, and we are gonna see details of it, shortcomings of it, and under what circumstances we should use it, etc. That will be the topic of this lecture. This is kind of a classical method. Nowadays people are not using naive Bayes much, but it is one of the basics, and I like you to know what kind of basic tools we have for this kind of classification. Later we are going to see more modern ways of doing text classification. We will be careful about a special instance, a special version of text classification, which is called sentiment analysis. Just a minute. Sentiment analysis. Sentiment analysis is the classification of a text into some sentiment groups. Sentiment analysis is a text classification method that classifies a given text into sentiment groups such as positive, negative, neutral, etc. And we will talk about it later at the end of this lecture. Okay, good. So one of the text classification, most popular text classification task is the spam detection. Given an email, we like to know if this email is a spam email or not. So if I receive such an email, would I consider this as a spam or not? Is a classical example of text classification, which is important because like maybe 10 years ago, receiving spam email was very common. Nowadays it is gone because the spam detectors are very successful nowadays. They are doing their jobs very nicely, very efficiently, very effectively. So all the spam is gone. So it is not a good business to be in the spam business nowadays, because if you are sending 1,000 messages as spam, only 10 of them goes to the intended target, which makes it very expensive to run a spam business nowadays. So spam detection using the right tools eliminated this whole evil business. Another practical method that is used by the another practical problem that is solved using the methods that we are going to learn today is this specific problem. the American history, United States history, there are some essays, okay, anonymous essays. They don't know who wrote them, okay. It is Madison or Hamilton. They don't know, okay. So the authorship of 12 letters are in dispute. They like to know who wrote them. So I need to classify those 12 letters to be Madison or, okay, Hamilton. We don't know. So how are we going to do it? So the idea is, let's study all the text written by Hamilton, Madison first, okay. I know that there are hundreds of documents written by Madison. I know that there are hundreds of documents written by Hamilton. And now I have 12 letters. I like to find which one wrote these letters, okay. So in 1963, these two people solved this problem using the methods that we are going to learn today. Again, people are wondering about what gender the author of this letter has, is male or female. Well, it's an interesting question, and we like to find it. And here is an example. Maybe you may guess. I'm not going to read it. Again, the sentiment stuff that I talked before. Okay. These are movie reviews. If somebody says it is unbelievably disappointing, it's a negative review. Okay, if somebody says that it is richly applied satire and some great plot twist, etc., positive. This is the greatest scribble comedy ever filmed. Okay, it was pathetic. These are all negative stuff. So I like to know which reviews are positive, which reviews are negative, and how negative, how positive they are. This is sentiment analysis. And another thing is the subject of the article. Okay, I have a paper, scientific paper or some other paper about some information, and I like to classify this into one of these, okay, groups. Why? Because if I am the journal editor, if I am receiving such articles, I like to automatically group them into these classes so that I can send them to appropriate reviewers, okay? If I do this automatically, I don't have to be an expert on everything to make this classification, and this classification is going to be done automatically by the system. Okay, this would be a very useful thing actually. Okay, remember, I mean, sometimes in our country, TÜBİTAK organizes some kind of a competition. TÜBİTAK says that, okay, I am accepting proposals for such and such projects, okay? And the project topics can change from computer science to material science to psychology to medicine to sociology, etc. So there will be maybe more than 200 categories of the project proposals. So somebody has to categorize them into classes so that if I receive 5,000 project proposals, I like to group them into appropriate groups, appropriate classes, so that I can evaluate them later with the proper evaluation people. So the topic of text classification is important. There are many applications, and that's where we're gonna look at. Okay, these are some of the stuff. Good. Okay, so formally, this is what we are gonna do. I have a document D. Okay, it's a document D. It will have, of course, it is full of natural language sentences. It could be a single sentence or it could be many sentences. Okay, and I have a set of classes from J1 to C1 to CJ, okay, J number of classes, and our predicted class is C. One of them is going to be picked. So this is my document. I am going to feed this text classification system, and it's going to produce a class number I, where I is between 1 and J. J is here. Okay, this is as simple as this box. So let's look at what's going to go into this box. Okay. As always, people, when they started working on this problem, they started using rule-based stuff. Okay. So when we do the spam detection first, maybe 20 years ago, this is how the rules are working. Okay. If I receive this email from a blacklist address, such as something.com, or if there are dollars in the subject line, or if there is this phrase have been selected in the subject line, I will mark it as spam. Okay, so I have lots of rules, this one or that one or that one or that one. Okay, using this, accuracy could be very high, especially if the rules are set by an expert. Okay, but as the new spam arrives, I need to update these rules. So who's going to do it? Humans are going to do it. That becomes very expensive in terms of human time. Okay, and when you add new rules, there might be some conflicts between the old rules and the new rules. So this is going to give me some problems if I am going to do all the rules myself. Okay, so this is like if-else cases. If this and this and this, spam, else if this and this and this, and spam, else if such and such and such and such, and then spam, etc. So think this as lots of if-else rule combinations. Okay, these are the hand-coded rules. The problem with this one is it is not easy to maintain such a rule set. And the other thing is that sometimes a single rule set doesn't work for all the people. Okay, if I am a banker, okay, I do my job on dollars, cents, etc. So if an email contains this word dollars a lot, that doesn't mean that it's a spam for me. It is my work. Okay, if it is my work, then this is not a spam for me. Okay, but as an academician, my emails unfortunately doesn't contain so many dollars. Okay, my emails, they are all about homeworks and projects and deadlines and that kind of stuff. Okay, so it changes from people to people. What I mean is that to maintain these rules, everybody has to do it by themselves, and that becomes even more expensive, and it is more error prone, because if you make an error, it is difficult to debug it. So hand-coded rules work at some degree, but they are not a very good very good solution. Okay, so what we are going to do is we are going to use supervised machine learning methods. That means that we are not going to write our rules by ourselves. Instead, we are going to find a function, a classifier, okay, a classifier that will take a document and it will produce a class. Okay, and we are not going to fill in that classifier ourselves. our machine learning system is going to do that. Okay, to do this, we need this information: a document, a number of classes, and we have this many documents with the corresponding class numbers. Okay, let's say M is 1000. I have 1000 documents. For each document, I need one of these classes. Okay, for the spam detection, classes are just two: spam or no spam. Okay, for the scientific document, for the scientific document subject category classification, number of classes is CJ. J is here, maybe 100. It might be a big number, very big number. So it changes from problem to problem. Okay, so a training set of M hand-labeled documents. Once I have this information, I have some standard algorithms. It will run on this data. Okay, given this data to me, I will come up with this function, and this function will classify a given new document into one of the classes. Okay, good. And what kind of classifier? And we are going to call this a classifier. Okay, we are going to look at this one. Okay, we will talk about this one too, and later we are going to look at this one and that one later. But nowadays, as I said, we will give our weights to naive Bayes first. But nowadays, the best classification methods use recurrent structures, deep learning, recurrent, okay, structures. Even the newest ones, they use transformer models. The transformer and recurrent structures, I am not going to talk about them today. We will talk about them towards the end of the semester, because they are about deep learning and I need to introduce some stuff. But we are going to look at this. We are going to look at these classical methods first, and then we will come to that later. Okay, any questions so far? Okay, the task of text classification was that, and let's look at the naive Bayes stuff. Naive, you know the meaning of naive. In Turkish, usually they translate it as acemi. Okay, acemi Bayes. Simple naive classification method based on Bayes rule. Well, we call it naive, but it may not be that naive because it works beautifully, especially for spam detection. Okay, and we call it naive because it relies very simple representation of document. Okay, we simplify the representation of the document and we call it bag of words. Very, very simple approximation of the document, and this is what it does. Let's say this is our text that we like to classify. Okay, I take this text, okay, words, okay, I take all of these words, I put them in a bag, okay, and I shake the bag. Okay, all the words are okay, they are still words, but they are mixed with each other. Okay, now I don't have the order anymore. I don't have the order of the words. Okay, so fairly, where is fairly in the original document? I couldn't see it. Where is always? Where is would dialogue? Can I see it? Scenes. Yeah, scenes here and scenes there, right? So I did not keep the order. I have lots of the word eyes, right? And they are all over. They change their position. The position is not important anymore. I mean, position is, of course, is important in the NLP representations, for Turkish, for English, any natural language, the order is very important, but with the bag of words representation, the order is not important. Of course, I am not going to use this as it is. I will extract this vector out of this representation. I will say that I have this vector where there are 6 it words, 5 I words, 4 the words, and 3 to words, and 3 and words, and 2 seen words, etc. So it becomes a very large vector. My vector is like that. Okay. If I have total of 40,000 words in English or Turkish, doesn't matter, 40,000, the length of this vector is going to be 40,000, and at the beginning, what is okay, here, let's say this word corresponds to test. Do I have test in this document? Yes, I have. I have 3 tests, and I have, how about the scene happening is 2 times, etc. So there are 40,000 numbers. As you may have guessed, if the document is this much, okay, there are many zeros in there. Okay, let's say a really seen word, for example, violation. Violation did not happen in this sentence, in this document, and it corresponds to 0 now. Okay, so this is the bag of words representation of this document. It looks like counting words again. It looks like 1 gram stuff, right? It looks like it is 1 gram, but it's a bag of words representation, we call it. Okay, so what are we going to do with this? Remember, our purpose is to find a classifier that converts a document to a class. We did not do that yet. We converted our document to a vector. So I took my document, okay, and I produce bag of words. I produce a vector. Now the document is like a vector, okay? It's not a document anymore, it's a vector for me. It's a vector, very long vector, but still it's a vector. Okay? And then here is my classifier Y. It will take this vector of 40,000 and it will produce a class. Okay. So instead of sending a document to this function, now I'm sending a vector, which is nice because if it's a vector, then I can write a mathematical function to come up with a class. It is either 0 or 1. Okay, it's a spam or no spam. Good,
Professor?
Good or not. Yes.
I have a question.
Sure.
Is this verse exist only full of the words like teach and teacher is different words for this test?
We had the same issue when we do the word counting for the 1 gram and 2 grams and etc. There are many different approaches and it depends on the language that you are using. For English, maybe teach and teaching are 2 different words. Doesn't matter much because in English, for a verb, you don't have that many forms. What can happen for a teach? Teach, teaches, teaching, taught. That's it, right? Only 3 forms. If I consider them as separate words, okay, that's no problem. Maybe my 40,000 vector is going to be 100,000 long vector, right? But for Turkish, when you come to öğretmek, öğrettim, öğrettiler, öğreniyorlar, öğretiyorlar, öğretilmiş, etc. So there are many forms of it. In that case, I need to take the root and do something about it because my vector becomes unbelievably large. I don't want to do that. Okay, so come to the original question. I don't have a definite or that way or this way. It depends on the language, depends on the application. Again, we are kind of ignoring that problem in this case. Why? Because it is the word counting problem. It is not the classification itself.
Thank you.
Okay. But again, I mean, I did not answer your question. It's a problem and it has to be addressed. Okay, good. With the bag of word representation, we need to come up with this function y, and for that one we are going to use naive Bayes. You know this formula, okay? This is a Bayes rule of a conditional probability, posterior probability, given the, what is the probability of C, okay? Given document, what is the probability of that document having a class of C? I could explain this using this formula. And in fact, the more general formula is this. Let me use the blue stuff. P C D is, okay, P C given D times P D, or I could write the same thing like that. P C D C given D times P C. Okay, so if you use this equation, you can come up with this one, no problem. Okay, this conditional probability Bayes rule is applied in many places in natural language processing or probability calculations, and in the many fields of artificial intelligence. I really like to know this. I mean, medical people use this a lot. Medical people ask this question: if symptoms, what do doctors do? They look at the symptoms and they make a decision on the diagnosis, right? If my first symptom is coughing, if my second symptom is high temperature, if my third symptom is tiredness, what is the diagnosis of this patient? Diagnosis of this patient: common cold. Common cold. Okay. I like to know this. Okay. And if I have a nice way of calculating this probability, let's say if I say that this is 80%, then my diagnosis is going to be you have a common cold. So what am I going to do? Just drink lots of water and get rest. Okay, that's what I'm going to do. Okay, our situation is going to be very similar. Given the document features, what is my diagnosis? Is it a spam email or it's a regular normal email? That's what I'm trying to do, the same thing. I mean, this is what doctors do, and this is the others that we are not going to, of course, we are not going to do diagnosis. We are going to do class assignment. And the nice thing is about, we are not going to say 1 or 0. We are going to say there is an 80% chance, there is a 20% chance. Okay, this is very powerful. Okay, because we will never say yes or no. Okay, we will say most probably or least likely. Okay, and for that one we are going to use this formula again. It looks like on the right the question is, given the document, what is the probability of this class? We are trying to find this probability, but on the right it talks about probability of the class and probability of the document. How can you let me ask you this question. How can you calculate a probability of a class? Let's say our task is spam or no spam. How can you estimate the probability of spam or no spam? Just a very simple prior question. What is the probability of spam? What is the probability of no spam?
We can determine it by the trained dataset ratios, spam ratio in all dataset tags.
Exactly. Remember, they are giving us, with the machine learning world, they are giving us, let's say M is 1000, okay? They are giving us 1000 documents, and they are saying that D1 is spam, D2 is no spam, D3 is spam, etc. So we say that out of 1000, 30 of them are spams. So P spam, maximum likelihood estimation of P spam is, okay, 30 over 1000. So I can calculate these classes. Okay, what is the no spam probability? It is 1 minus 30 over 1000. So this is prior probability. Okay, prior probability. Prior means that without knowing anything, I don't have anything given. What is the probability of a given email being spam? This is very much like this. What is the probability of diagnosis being cold? I don't get anything. I don't see the patient. Okay, what is the probability of a patient having a common cold? I mean, for this one, I would look at the statistics. I look at the statistics. I know that given a time, 0.1% of the people have this common cold. I know this. So this is called prior probability, not posterior, but prior probability. This is posterior probability. Posterior probability is conditional. Says that given this document, probability of having a spam. Given that patient has cough and high temperature and tiredness, probability of cold. Okay, so this is much more interesting than this one, because this one has the evidence, this one has the observation, this one doesn't have those, this one has just training data. Okay, and this one is interesting. Why? Because, I mean, without seeing the email, all I can say is that there is a 0.03 chance that you are going to receive a spam email. But after seeing the email, I would say that there is only a 5% chance that this is a spam email. Okay, so this is much more powerful than prior probability. Okay, good. Let's move on. So this is what we're going to do. I will run this for all the classes that I have. If I am doing spam, no spam, okay, if I am doing spam, no spam classification, or if I am doing Hamilton or Madison classification, number of classes is just 2. But if I am doing, let's say, sentiment analysis, very positive, positive, neutral, negative, and very negative, then I have 5 classes. Okay, then I have 5 classes. So I am going to run this probability estimation 2 or 5 times depending on my application, and I will find the maximum probability, the class that produces the maximum probability, and I will say that that's my class. That's what it means, right? Argmax. Find the argument C that makes this probability maximum. Find the probability that makes this probability maximum. But I know that this one is equal to this one from the Bayes formula. This one is equal to this one. And it says that I would drop the denominator. Can somebody explain it to me why we are dropping the denominator? It says that this one is not important. Why is not important? I mean, I need to divide this multiplication by PD. It says that PD is not important in this case. Well, PD is definitely important to make a calculation for this probability. But it looks like for the sake of calculating this maximum a posteriori calculation, most likely class calculation, PD is not important. Can somebody tell me why PD is not important?
Because I think it's all the same in all of the classes, and since we are looking for the maximum, we don't need to do an extra calculation for that.
Yes, exactly. We are here to calculate. We are here to estimate the class that makes. Yes, exactly. What Ahmed says, we are here to calculate or estimate the class C that makes this probability maximum. I don't need to calculate the exact probability, okay? All I need to find a C that makes this maximum. Since whatever the value of C is, PD is not going to change because document is fixed. They are asking me this question. I am going to give you a document and you are going to give me a class. Okay? I don't need to calculate PD to find the class that makes this calculation maximum. That's why I dropped it. So this one is important. Okay? The probability of C class times given C probability of D. We kind of flip the question. We used to ask this question. Given the document, what is the probability of C? Now it is just the opposite. Given the class, what is the probability of this document? Okay, so I know how to calculate this one. Let's look at this one. I know how to calculate that one, but let's try to understand the meaning of this part actually. Let's try to understand the meaning of this part. It's just the opposite. It says that given spam, given spam class, what is the probability of this email one? Okay, the class spam is given. It looks like produce me a spam email kind of thing, right? Very, very different question. Let's ask this question to the doctor, medical doctor. Given that my diagnosis is cold, the patient has cold, what is the probability that the patient shows coughing? Okay. How can I calculate this one? It is not that difficult. Out of all the patients that have cold, out of all the patients that have cold, I would count how many of them are coughing, and that will give me my map estimation, right? That will give me my MLE estimation of the p-value, maximum likelihood estimation of the p-value. So it's kind of this. This disease is causing cough. Okay, this spam letter, spam classification is causing this email kind of thing. So it's kind of cause-effect relationship. Given the cause, what is the effect kind of relationship? And calculating this is much easier than calculating that one. Okay, calculating this is much easier than that one, because this one is cause effect. Okay, if this is the cause, if it's the root cause, this is resulting in this effect, I can make better predictions about that one. Okay, so we like this one better than the other version. That's what naive Bayes is doing as the first step. Just change the question, reverse the question, so that it does that. Okay, so here our CMAP is going to, let's not, I keep saying the things like MLE, maximum likelihood estimation, and maximum posteriori. Okay, this is most likely class that maximizes this P. To calculate the P, we could use maximum likelihood estimation, which is what we did with those 1,000 emails and 30 spams and etc. Okay, and we don't have to use this maximum likelihood estimation to calculate P, and you have seen this when we did the language modeling with the when we did the language modeling with the n-grams and the statistical language models. Remember, we have used smoothing. When you use smoothing, MLE doesn't work very well, and when you use smoothing, it changes the results. So we are going to do that too. Okay, and we know that my document is this. My document is composed of n words. Okay, there are n words in my document. Let's say there are 100 words in my document. This is my first word, second word, third word, and the 100th word. Okay, given spam, what is the probability of having these words in this order in a spam email? Okay, that's the question. That becomes a question. Okay, so calculating this is not that easy. Okay, calculating this is not easy. Why? Because I need to see an exactly same email before. Okay, and it has to be, let's say I have an email, this email. What page is this? Okay, this is page 22. Let me go to the beginning. Remember this one. In this email, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, let's say 100 words in it. Okay. To be able to calculate given spam, these x1 is going to be subject, x2 important, and ... x100 is reserved. How would I estimate this one? I would estimate this by looking at all of my spam emails. Okay, inside my spam emails, how many spam emails I have, and how many of them is an email like this. Okay, how many of them is an email like this? Exactly the same email. This is not easy to calculate because I may not have received this email before. Usually they change their emails a little bit so that I don't match it exactly. So calculating directly this is not that easy. You need a very, very large data set. Okay, and that data set has to be marked by hand so that I know what class it has. So this is not a good idea to do the maximum likelihood estimation this way. Okay, I could only estimate, okay, if a very, very large number of training examples was available. Okay, and so that like we did before, we are going to do, and we run into this problem before. Remember our 5 grams and 6 grams and 7 grams. Remember, we cannot calculate them. Even Google cannot calculate it reliably. 10 grams. Okay, and we are talking about 100 grams here. This is much more complicated. So we are going to do some kind of an approximation. That's where the naiveness comes from. Okay, the assumption is this. Okay, multinomial naive Bayes independent assumption. It says that assume this. Assume that the words are not dependent to each other given the class. Given the class, words are not dependent to each other. They are dependent, but given the class, they are not dependent. That's what we are saying here, conditional independence. So this is not exactly equal, but approximately equal, given the assumption. Okay, assume the feature probabilities are independent given the class C. Okay, this is bags of words assumption. So it means that as long as I have some word in my email, that's the important information for me. Okay, that's the important information for me. I like to give an example. Let's say, okay, let's try to calculate this one. Let's say my document is very, very small. Let's say x1 is x1. It's just 2 words. My document is very good. That's it. Okay. The first word is very. The second word is good. And let's say instead of doing spam detection, let's say sentiment analysis. Is this a positive message or negative message? Let's say it is positive. Okay. So how can I make this calculation? Of course, using the bias rule. Remember the bias rule again? Let me. PAB is equal to P given B times PB times PBA, or PA PBA. Okay, so doing this, maybe I can just do the math, and PAB is PA comma B over PB. So what am I going to do here? It will be probability of positives and probability of very good positives. So how am I going to calculate this one? I will count all the positive messages, and I will count how many of them contains this very good sentence, very good. Okay, this is how you calculate them. But this one says that no, don't do it that way. Okay, this one says that Don't do it that way. Do it this way. How is this doing? This one says that, okay, to calculate P very good positive, do this multiplication. Given positive very times given positive good. Okay, so find and divide them by positive, but I don't need to use this positive thing because it doesn't change my results in terms of finding the class positive. So but if you like, I can of course divide them P positive here. Okay, so let's try to see the difference between that one and that one. This one says that all the positive documents, how many of them contain very good? This one says that all the positive documents, how many of them contains very times all the positive documents, how many of them contains good. Okay, they look kind of similar. Okay, this one counts them together, this one counts them separately. Do you think they are approximate? They are conditionally independent? Do you think I can assume the same thing? I mean, either I would calculate that one or that one. Okay. Let me try to take this out and write it the same way that I have written here. Just erase it. Okay. Like that one. Duplicate it. Put it up. Instead of doing, no, didn't work. Control Z. Okay, so do the same thing here. Instead of doing this, let's write it the other way. Okay, P very and positive same time, P times good and positive. That's it. Don't calculate this one, but calculate this one. Okay, it looks like we are over time for the first part of the lecture. Think about this one. Okay, let's try to compare this one with this one. And are we losing anything? Because there is an assumption, conditional independence assumption. If we are not losing, then what is this assumption is giving us and taking away from us. Okay, let's take 10 minutes of break. We'll be back at 14:33. Okay.
işareti. Bir bakayım. Acaba sağlansa mı, ne yapsa? Geçen hafta yapamamıştık değil mi? Geçen hafta. Yapmış mıydın?
Yaptık. Sabah yaptık
Ya
ya.
sen çok unutkanlık ya. Şimdi ben oldum öyle. Sırayla ne?
Yaptık hatırlıyorum ama.
Ben hatırlamıyorum.
Yapmamış da olabiliriz. Ama yaptık ya.
Ondan önceki hafta yapmamıştık.
Ondan önceki hafta yapmadık.
Onun için biraz bekleyin.
Hatta atmıştı ya.
Ha.
Hocalar diyorlar ki bu bunu yapmayacak diyorlar benim insanlarla. O zaman sizler birleştirmek.
Cam komple açayım mı?
Aç kurusun.
Kolay
Ben hocam.
Ben diye girerse ben...
Hemen siz gidince hemen böyle.
Ben ara vermiştim ya.
Biz diyene kadar çıkalım dedik ama çıkamadık hocam.
Tamam.
Yakalandık sana.
Uzaktan eğitim oluyor hocam. Keşke uzaktan temizlik de olsaymış.
Yapmazsanız uzaktan eğitim olur mu?
Ben 25 senedir her gün işten çıkıyorum hocam. 25 senedir hiç bir türlü sevmedim iş hayatını.
Sen de daha çok çalışman lazım.
Evet işte değil mi? Bir emek var.
Ev aldın daha çok çalışıyorsun.
Ben de ya.
Okay, so let's go back to my original question. We are saying that, okay, let's not forget about this p pos stuff, square of it. Okay, instead of calculating this, we are calculating this. We are saying that given the class positives, good and very is not dependent each other. Okay, if the class is positive, counting very and counting good differently, separately, would be good enough for us. Okay, and it makes kind of sense because very is a positive word and good is a positive word, and doesn't make much difference if I count them together and if I count them separately. But one bad example is not good. Okay, so if I count this at good, okay, in a positive email, in a positive message, I see lots of goods, but not good is not good, right? Maybe it sounds funny, but not good is not good. Because not and good depend on each other. When I say not good, I am not meaning anything that is good. Okay, so in these kind of cases, this naive bias assumption of conditional independence will fail. But still, we are going to continue and we are going to say that this is good enough approximation, and we are going to follow this one. So I am going to make these simple calculations instead of finding one complete email that is the same as my input email in my data set. I will start doing this with the single words only, and that's going to be good enough for me. So using the idea of naive bias, conditional independence. Okay, multinomial means more than two classes. Okay, as many as classes you like. To calculate this one, you don't have to calculate this whole thing. Okay, you don't have to see the whole email or whole message before. Seeing the words only should be good enough. Seeing the words only good enough. So calculate this one instead of calculating that one. And do this for each word. See, the capital letter X means it is this document. And for each word, calculate this and multiply it with the probability of the class, and find the class that makes this probability calculation maximum. This should be CJ and this is CJ. Okay, good. Any questions so far? That's what we're going to do. So maybe we'll go into details of what we're doing by this calculation. We get a new document, a test document. We call it test document. Okay. And in all the positions of test document, this is my test document. Positions I from 0 to, let's say, n. Okay. These are my words. There are n words in it. So I starting from 0, okay, position number 0, and I will go to up to n minus 1. Okay, and my classes will change from class number 0 to class number k, whatever my classes are. For the sake of simplicity, let's say I have only two classes, positive and negative for the sentiment analysis, or spam or no spam for the spam detection. Okay, so J will change from 0 to 1. Class number 0 is spam. Class number 1 is no spam. And my I will change depending on the document from position number 0 to position number n minus 1. So for each word, I am going to calculate this probability. I am going to calculate this probability given the class 0. What is the probability of seeing giving class 0, let's say giving spam? What is the probability of seeing dollars? In a spam email, we see lots of dollars, right? Okay. In a spam email, we see lots of fortune, lucky, etc. Free, etc. Those are spam email words. Those probabilities will be high. Okay, good. So we are gonna see a few examples, and we are gonna see how to make those calculations. And there are some issues with those calculations. So this one said that we need to calculate it given Cj, probability of xi, and probability of Cj. Let's see how we can calculate it. Maximum likelihood estimates, MLE. Okay, remember that MLE, we use MLE for making an estimation for these probabilities. What is the probability of having this class? Okay, so this is what is NDOC? What is NDOC? Can somebody tell me? NDOC?
Number of documents.
Number of documents, exactly. Let's say I have 1,000 emails, okay, and spam is 30 of them. No spam is 970. So this one is C0, this one is C1. So the maximum likelihood estimate of PC0 is going to be 30 over 1,000. Okay, and that's the first part. Remember our formula, R max, the class C that makes this probability maximum. Okay, C and W. This is okay. This is CJ, J, this is I, and I is all the positions. That's what I'm trying to find. So to calculate this one, maximum likely estimate says that let's look at the upper part first. Nominator. Can somebody tell me what this is? What is this?
Number of where Wi and Cj occur together.
Yeah, number of Wi and Cj occurs together. Means if I give you an example, let's say Cj is spam, okay, and Wi, let's say free. The number of times the word free occurred in a spam email, okay, number of words that that free and spam email occurred together, and the denominator, the lower part is in spam documents, okay, this is all the vocabulary, right? Count of all the words in that spam documents. Okay, how many words do I have in all the spam documents? So this is a very small probability, right? So you would expect that free happens a lot in a spam document, but there are many other words happening in a spam document. But this is a very, as I said, this is a very small probability. Again, this might be a very small probability, and we are going to calculate lots of them. We are going to calculate lots of them, and calculate each one, multiply with each other, and you are going to have your final results. The probability of this email being a spam or not. Okay, so this is explanation of that one. Fraction of times the word WI appears among all words in a document of topic CJ. To calculate the lower part, this is the suggestion from the book. Okay. To calculate the lower part, this is a suggestion from the book. It says that put all the documents that belongs to topic J, that is the spam emails, in a document. Okay, let's say out of those 1,000 documents, remember 30 of them spam. So make a spam.txt that will contain these 30 documents, and make another document that will contain no spam emails, no spam.txt. So the book calls it mega document. Okay, so we will have, for our spam no spam example, we will have 2 mega documents. We will have 2 mega documents. One for the spam emails, one for the no spam emails. Okay, and U frequency of W in mega document. What is V? What is V? Not W, but V. Here, what is V?
Over.
Ahmed, I did not get what you said.
Any word?
Any word? Any word in where?
Does it beg of words vector?
V is the set of all words in my dictionary. Okay? V is the set of words in my dictionary. So I will do this for all the words in my dictionary. It's kind of an expensive thing. Okay? Okay, so this is good. Okay, easy to, it might be a little bit expensive, but it is good, easy to calculate, as long as I have the resources and etc. But the problem is this. Some of the words in my dictionary, okay, will not happen in my mega document. It will not happen. It's not because it is not likely or it is not impossible, but it will not happen. Since this is a multiplication, if one of the words is a word that I have never seen before, that's going to make this multiplication 0. When the multiplication becomes 0, the probability becomes 0. And I don't like that, okay? As I said at the beginning, I like my probability to change between 0 to 1, but I don't want to see zeros, because no probability is going to be 0. I mean, any email could be although with a very small probability. Any email could be a spam email, right? So I don't wanna do that, especially not for the reason that one of the words did not happen in my data set before. So what are we gonna do? We are gonna do this smoothing thing again. Remember, we had the same problem before. The fact that you have never seen that 3 gram before doesn't mean that it is not possible. It most probably means that you did not see it. If I didn't catch a certain kind of fish, that doesn't mean that that fish doesn't exist. It might most probably mean that you didn't catch it. It's as simple as this. Okay? If I have never seen the word fantastic in my positive reviews, so the count of fantastic will not be seen. This is 0. Since this is 0, this whole number is going to come back as 0. And if this is 0, if I put this in one of the multiplication numbers, my argmax is going to be 0 for this probability. I don't want to do that, okay? 0 probabilities cannot be conditioned away no matter the other evidence. So just because there is a word that I have never seen in my email should not make my email probability of 0 for the spamless test. We need to do something. So what is your suggestion? What should we do? Somebody make a suggestion to prevent this problem. MLE will not work. MLE is good, but for the counts of 0, I will have problems.
What if we try add one smoothing again?
Exactly. We could do advanced smoothing. It is simple enough. So we would add 1 to the upper part, add 1. But if I do the add 1 only, that will mess up all of my probability calculations. So I need to do this adding of the number of elements in the dictionary thing too. Okay, that was add one smoothing, right? That's how we call it, advanced smoothing. Okay, so whatever this count is, always add 1, and always add 1 to all the counts of W and C. If you do it V times, it becomes this. So this is Laplace smoothing or advanced smoothing for naive Bayes. As you may remember, this was screwing up all of our calculations, count calculations for the large numbers, but we will ignore that for a moment, and we are going to use this assumption of smoothing so that we don't end up having 0 probabilities if we have seen words that are not seen before. Okay, advanced smoothing. Good. Okay. So if we go back and if we try to remember what we did before, okay, 2 important things. One is PCJ, okay. The other one is the calculations of the, remember it was like this, PCJ times all the multiplications of CJWK, and K is from 0 to all positions. Okay, so given the our corpus, our 1,000 documents, 30 of them spam and 970 of them are not spam, we are going to do this calculation for each class in my class set. Okay, so I am going to do I am going to do these mega documents, concatenate all the documents of a given class, okay, and I will do this counting, okay, what is the probability of this class, okay. So this concatenation is here. Text J is the text document for class number J, and for each word in my vocabulary, in my dictionary, okay, I will calculate this one. NK is the number of occurrences of WK in text J. Okay, I have class number of classes, number of mega documents, and this is my calculation. It looks like instead of using 1 and 1, okay, I am using an alpha, okay, so that it is not add 1 smoothing, it is add alpha smoothing. I need to, if alpha is 1, it becomes exactly the same as before. If alpha is less than 1, so its effect is a little bit smaller than the advanced smoothing. So the bad side effects can be taken care of, maybe. Okay. So this is from our training corpus. And that's one example how we can do the text classification training. When the test times comes, we are going to do the similar calculations. Okay, let's stop talking about this text classification for a minute, and let's try to see the similarities of this naive Bayes and the language modeling, statistical language modeling. Remember what we did with the statistical language modeling? Given a sentence, let's say my words x1 to xn, I go to school very early. Okay, so with the language modeling, I can make an assignment to this probability estimation, and we call this statistical language modeling. And we are gonna see that actually with naive Bayes, we are doing probably a similar thing. Okay, two things are related. Okay, two things are related. Let's say we have a task that given a document belongs to, okay, I have two classes. Class 0 is China and class 1 is Japan. Two classes. Given a document, I like to assign a label to this document. It's either China document or Japan document. Okay, China document or Japan document. And I am going to do the naive Bayes assumption again. Okay, so I have all the given China, what is the probability of Shanghai? I know this probability. Given China, what is the probability of seeing and? Given China, what is the probability of Shenzhen? Okay, etc. I know all of these probabilities. Okay, so since I know all of those probabilities, given a new document, I can calculate the probability. I can estimate the probability using the smoothing techniques, of course, that this document belongs to China document class or the Japan document class. Okay. If I do this, I am doing something very similar to language modeling. This is what I do. Okay. Assigning for each word, okay, I give this probability. I give this probability. So from China example to again positive to negative example, if my sentence is I love this fun film, okay, I love this fun film, and I know that my class is positive, given positive, what is the probability of having I? This one. It turns out to 0.1. What is the probability of love? This. I keep multiplying these values, right? So at the end, I obtain a probability like this. So this is a language modeling, but conditional language modeling. I say that given that I know this message is a positive message, what is the probability of seeing this sentence? Okay, so I ended up obtaining some kind of a probability for this sentence. But this sentence is not an ordinary sentence. I know that this sentence is a positive sentence. I know that this sentence is a positive sentence. Okay, so this is related to language modeling. Of course, it's a special case of language modeling. It is not regularly, given an unconditional language modeling, but the conditional language modeling. Also, there is another important difference. See, in this case, doesn't matter I comes here or there, okay? I can change their positions. My product will be exactly the same. So this is very similar to actually using 1-gram language modeling given the class. 1-gram language modeling using the class. So it is unigram language modeling. So for each class, I have a language model. For each class, I have a language model, and these two concepts are related to each other. Of course, if you measure the perplexity of this model, the perplexity will be very high because it is using unigrams. Okay. That's why we say that measure the probability of this sentence for the positive language model. So I am seeing it as how many classes do I have? 2 classes, positive classes and negative classes, okay? I am going to have a language model for the positive class, and I am going to have a negative model for the negative class, language model. And given a new sentence, I will measure the probability in 2 different language models. Whatever the model is, whatever the probability is going to be my decision, either positive or negative. I could do the same thing for Turkish and English. Okay, let's say class 0 is Turkish and class 1 is English. Okay, just take 2 very large sets for Turkish text and the English text. Okay, one of them is class 0 and one of them is the C English. And I have a language model for Turkish and I have a language model for English. Given any sentence, do these calculations, and whoever probability is greater, then you will say that this sentence is a Turkish sentence or English sentence. Okay? Without knowing the language, you can make these kind of deductions. Okay, so let's close the parentheses. Okay, I did this while I was talking about naive learning training. I opened the parentheses. Okay, now I am closing the parentheses. Relationship to language modeling. Okay, so let's look at this example, the Japan China example. Okay, our data set is very, very small. I have only 1, 2, 3, 4 sentences, 4 documents in my training set, And of course, I have two classes only, China class and the Japan class. And I have only one test case. Very, very simple, stupid example. Okay. So remember, I need to calculate these maximum likelihood estimates, PC, for each class. For China, it is 3/4. For Japan, it is 1/4. Why? Because out of 4, only three of them are China, but only one of them is Japan. Okay, so I did that. Remember, again, PCJ times P given CJ probability of WK is element of all V's. This is what we're trying to find the multiplication of. Okay, so the conditional probabilities for all the words in my dictionary. How many words do I have in my dictionary? Can somebody tell me? How many words do I have in my dictionary? I am not saying how many tokens do I have in my corpora. I am saying that how many words there are in my dictionary.
6.
6. Okay, let's count. Chinese is 1, 2. I already counted it. 3, 4, 5, 6. I think the rest is, yeah, okay. There are 6 words in my dictionary. Okay, so the conditional probabilities for each word, for all the classes, will be calculated. Okay, for Chinese, given China, probability of Chinese. Tell me how they calculated this one. What is 5? What is 1? What is 6? And what is 8? What is 5?
Number of Chinese words in China tagged documents.
Number of times the word Chinese happened in the China dataset, right? So in this case, this is 1, 2, 3, 4, 5. What is 1?
The one in Japan tagged document. Chinese that tagged Japan.
No. 1 is due to smoothing. Okay, Laplace advanced smoothing. All of these ones with the green, these are all advanced smoothing stuff. Right? So these are advanced smoothing. And similarly, what is 6? What is 6?
Vocabulary number.
Yeah, due to the advanced smoothing again. So this, let me do this. This 6 is this, and this one is this one. Okay. Okay, let's go back to the calculation. 5 is number of Chinese in China. 1 is advanced smoothing. 6 is advanced. What is 8? What is 8? Eight should be the number of words in my China documents, right? And how many of them I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There should be 11. Why is it saying 8? So there is a problem with this thing, okay? This should not be 8. It should be 11, because there are
Sir, the last class is Japan class.
Oh, sorry. I should not count this one. Yeah, okay. It is 6 plus 3 plus 3 plus 2. Yeah, it is 8. 8 is correct. So there are 8 words here and there are 3 words there. Okay. So this 3 is this one and this 8 is this one. So I did these calculations and I have calculated the conditional probabilities for Chinese, Tokyo, Japan, Chinese, Tokyo, Japan, for these classes. How many words do I had in my vocabulary? 6 words. And I did not calculate Shanghai for the... Okay. I did not calculate the Shanghai given China. I did not calculate Macau because for my test case I don't have them, right? For my test case there is only 3 words: Chinese, Tokyo, and Japan. Okay. So if I do this calculation, given the test case D5, Chinese, Tokyo, Japan, this is 3 over 4. What is 3 over 4? What is 3 over 4?
Chinese tech documents in all training sets.
3 over 4 is exactly 3 over 4 is this. Okay. Probability of Chinese, 3 of them, okay, out of 4. What is 3 over 7? 3 over 7 is this one times 3 over 7 times 3 over 7. Why? Because I have seen this Chinese 3 times in my document. 1 over 14 is this 1 over 14 is this one, and this 1 over 14 is this one. So the probability of this sentence in the China dataset is 0.0003. If I do the same calculations for the Japan set, it's going to be 0.0001. Okay, so what would I say? I would say that this sentence seems like it belongs to a China dataset, China class. Okay, very stupid example, doesn't mean much, but in order to show you the results, to show you the steps of what we do with the training and what we do with the runtime, this is a good example. And without doing the Laplace smoothing, as you see, I cannot make these calculations, because without the Laplace smoothing, Tokyo and Japan. Tokyo and Japan have never occurred in the Japanese set, Chinese set, right? So their counts come back as 0. Without adding these 1.0s, these would have been zeros, and this calculation would make 0. I don't want that, because in that case China probability would be 0, and which would produce me the wrong result, right? So I don't want to do that. So the smoothing worked, and it gave me logically correct result. Good. Any questions so far? Okay. With the naive bias in spam filtering, it is used very much all the time. Most popular spam filters, for example, the spam assassin, it uses the naive bias stuff, but it doesn't use the words only. Okay, it uses many features. I mean, remember when we say this one happened, I mean, it just multiplies lots of probabilities with the word probabilities. Some of those are features, okay? Some of them are features, like some of the, for example, if the from starts with many numbers, if subject is all capitals, each HTML has a low ratio of text to image area, these kind of features, and we multiply these kind of feature probabilities with the other word probabilities. Okay, so it is used in spam filtering. So at the end, naive bias, we call it naive bias, but it is so naive. It is not so naive. It performs very well. It is very fast. Low storage requirement. Why it is low storage requirement? For each word in my dictionary and for each class, I need to store a double number. Okay, I need to store a double number for each word and for each class. That's my memory requirement, low storage requirement. And it is robust to irrelevant features. What do we mean by this? What do we mean by this? Robust to irrelevant features? What's an irrelevant feature? Let's say I have a sentence. In a sentence, sentence 1, ... and ... okay, and sentence 2, ... and ... and is irrelevant. Why? Because and is not going to change my final results. But I will have to somehow measure, given spam, what is the probability and given no spam, what is the probability and I expect that both of them will be equal. Okay, both of them will be equal. So if I multiply both calculations with the same number, okay, it's not going to change my final results. Okay, that's why it says that these are irrelevant, and irrelevant features going to cancel each other without affecting the results.
Can I ask a question?
Sure.
If it's not going to affect the result, why do we filter the stop words in text classification project?
Usually they do. Usually they first remove these kind of words and, or, I, you, email, etc. Okay. Usually they remove these kinds of words because even though they are not going to change the results, I don't want to calculate them because I like to be efficient. But you need to make a list of stop words or the irrelevant word first. That will take some effort, right? And I don't want to spend that effort. I mean, without doing that stop word elimination, I expect that these kind of things will not affect my results anyway. So I can spend maybe a few more CPU cycles and get the results the same as with the stop words. Okay. So usually they do though. Usually they say that these words I know they will not make any difference. Okay, the from or subject. Every email has a word that starts with from or subject or to, right, or carbon copy. Okay, calculating these probabilities for those words doesn't make any difference because they will produce exactly the same thing.
Does filtering this kind of words helps us to understand which words are much more important for our documents? I guess it's changing the frequency because when we filter this kind of words, and we can understand the importance of others.
Well, if you filter these out, if you don't consider them at all, your final calculations will be more robust. But as I said before, I mean, sometimes I mean, for and I and you and email, it is easy to make this decision, but there are some words, it is not that easy to make that decision. Okay, so the naive Bayes is actually will be optimal if the conditional independent assumption hold. Okay, naive Bayes says that the probability of given a sentence, given a spam, probability of not, okay, will not be affected if I have such a thing in my sentence. Okay, not good should be paid more attention to, and the naive Bayes says that not and good are completely independent, although in real life it is not. So we are going to see some examples of it. So it is optimal if independence assumption hold, and I know that it doesn't hold, but that assumption is powerful enough to make our final results good enough for the text classification. Okay, good. Okay, so we looked at this result, and let's look at how we measure our performances, how we did with the naive Bayes classification. But before that, I like to take 10 minutes of break. Let's be here around 15:32. Okay. So some of you may have seen this before. Precision recall and F measure metrics to measure our success. We have a text classifier. How are we doing in terms of our performance, objective performance? And let's try to see it again. Let's say again I have 1,000 documents. Okay, 30 of them are spam and 970 of them are no spam. Okay, I have this. Usually this is what I do. Usually I randomly select 900 of them for training, 90%, and 100 of them for testing. Okay, so I use this 900 for getting the class probabilities and given class the word probabilities, and for testing I use these probabilities to test. Okay, when I test the documents, okay, for each case I will increment one of these numbers in the 2 by 2 contingency table. This is called contingency table. Okay, let's say I tested one of the documents. Okay, I know that it's a spam document. I tested it and it correctly said that it is a spam document, so I incremented this true positive by 1. If I test something and if it say positive, okay, it's a spam, and it is correctly said so, then it's a true positive. True is something good. Okay, if I know that a document is a regular no spam document, okay, and I tested it and it said that it is not a spam document, so it is correct. Again, true negative. It said that it is no spam, it is true, and I know that it's a true negative. Let's say I test the document, I know that it is a spam document, but it said it is not a spam document, then it is false negative. If it's a spam but it said it is no spam, it is false positive. False is very bad thing, it's a bad thing. True is the good thing. So I expect this table in my case, let's say 100, let's say out of 100, let's say 3 of them, come on, 3 of them is spam and 97 is no spam. I expect for the best case, there is no false positive, there is no false negative, 3 true positives and 97 true negatives. This would be the base case. Okay, so these 4 numbers are good, but I like to express them with numbers between 0 and 1. Between 0 and 1. Okay, so maybe I can look at accuracy. How about 3 over 100? Well, I am detecting everything out of 100. Doesn't mean much because it doesn't talk about how many question I asked and how many is them possible. Okay, so this is not much because although I am doing as good as I can, 3 over 100 is not a good number. So what they did is they developed this notion of precision and recall. Okay, precision and recall. Precision says that number of selected items that are correct. Okay, number of selected items that are correct. Recall is number of correct items that are selected. Okay, and when I show you the formulas, it will be clearer. Didn't I put the formulas in here? Oh no. Where are my, okay. And I'm directly giving you the okay. Maybe the formulas are I think I took them out. Okay. Precision is number of items that are correct. And recall is number of correct items that are selected. Percentage of correct items that are selected. So the percentage of correct items that are selected is true positives plus true negative that are false positives. So the true positives over true positive over that are selected. True positive plus false positives. Okay. This is recall, and the other one is true positives over true positives over true positives plus number of selected items that are correct. Selected items. Okay, and this one is false negatives. Okay, so it looks like we are adding these two, and we are adding, okay, maybe do it this way. Blue is this, and green is this. Okay, here. Okay, one is precision, one is recall. One is concentrating on the percentage of selected items that are correct, and the other one is percentage of correct items that are selected. I mean, how many selected is important. Precision and recall, they are not always in agreement. They are kind of a trade-off. Okay, they are kind of a trade-off. What do I mean by this? There are ways of increasing precision without increasing the recall, or there are ways of increasing the recall without increasing the precision. Okay, if there are no false negatives, okay, then TP over TP would be 1.0. Okay, if there are no false negatives. If there are no false positives, okay, then TP over TP again becomes 1.0. But I like both of them, false negatives and false positive, to be 0, because I don't like those numbers. I don't like this number, and I don't like this number. If I make one of them 0, okay, either precision or recall will not get affected from it. If I make both of them 0, that would be the best. Okay, that would be the best. The best thing is, of course, both of them are 0, but in real life this is not going to happen. In real life, I will see some numbers here, and I will see some numbers there, and each one will affect one of the calculations of precision and recall. Okay, good. So this is what we call precision and recall, and sometimes we don't want to express our results in terms of two numbers, so they have they came up this F measure. F measure puts them together, precision and recall, in the same formula. Let's say this beta. Let's take beta as 1. In that case, if beta is 1, this F measure becomes F1 measure, and F1 measure is this one, 2PR over P plus R. If in the perfect case, if P and R are 1.0, 2 times 1 times 1 over 2 is 1. Okay, 2 times 1 times 1 over 2 is just 1. So in the perfect case, F becomes 1.0. Okay, in one of the bad cases, where P is very, very small, if P is very, very small, okay, the upper part will be very small. Doesn't matter what R is, F value is going to be small. Okay, so F measure is a measure that considers both precision and recall. Okay, how do I make P or R 0? If your true positives are 0, then both of them are going to be 0. If false positives are very, very large compared to false negatives, okay, they are very, very large compared to false negatives, then your recall is going to be very small. And if your recall is going to be very small, then in that case, this F number is going to be small. Doesn't matter your precision is large, close to 1. Okay, so these are the two things that we use to measure our performance, precision and recall, in terms of classification out of this contingency table. We don't use these 4 numbers by the number like this 970 or 30, something like that. We like to see numbers that are between 0 and 1. Okay, so with the evaluation, if you have more than 2 classes, okay, that was 2 class case. Okay, spam, no spam. You can make a mistake, or you don't make a mistake. Okay, those are the 2 classes. Set of binary. Okay, if you have 2 classes, then we are fine. But if you have more than 2 classes, let's say it is a positive, very positive review, positive or neutral, or maybe I should say neutral. Okay, for the neutral, let's use T. Neutral, negative, very negative, 5 classes. If I have these 5 classes, then I cannot use the binary classification as it is. So one of the methods is any of or multivariate classification stuff. Okay, for each class I have a classifier. I have a classifier for very positive. I have another classifier for positive, another classifier, another classifier, another classifier. There are a total of 5 classifiers. Okay, there are a total of 5 classifiers, and I run each classifier on each of the test cases, and whoever produces the largest p-value in naive Bayes will get my vote. Okay, will get my vote. So it is called set of binary classifiers. and with the set of binary classifiers, I evaluate 5 of them. The one that has the maximum score will get my result. Okay, here we are talking about a data set, Reuters data set, that is used for this kind of classification tasks a lot. In this data set, okay, there are more than 21,000 documents. Okay, and in these documents, 90 classes and 200 subclasses. Some people divided these documents into test and training cases, some of them, not all of them, but some of them. This set, Lewis split set, is doing this. It says that, okay, you are going to use this 9,600 for training and these 3,299 for test, and I'm going to give 118 categories for this test set. Okay, and one article can be in more than one category, and these are some of the categories. These are not very clear categories actually. That's why we say that one document can have more than one category. In fact, in this split, each document on the average has 1.24 classes. Okay, 1.24 classes. So it is not a single label assignment problem. Yes, Selmani says, is it? Yeah, well, what do you mean? It is 118 binary category distinctions. So these are the number of classifiers that you're going to have, 118 binary. Okay? It is binary. It is still... This number is correct. Okay? Each document has, on the average, 1.24 classes. Okay? And for these documents, more than one classifier should say, okay, I have it. I am giving a positive for this one. Classifiers are binary, but the documents doesn't have to be exclusively binary classified. Okay, this is one example out of that data set. As you see, these are the topics: livestock and hog. And I think this is, yeah, this Lewis split says that this is for training. There are other splits, CGI split, this is for training. And these are some IDs and title and the body of the news. And it has 2 categories. Okay. And once we do that, since we don't have just 2 categories like spam, no spam, instead of that 2x2 contingency table, now we have confusion matrix. This is called confusion matrix. Confusion matrix is this. Let's say an article belongs to the poultry. Okay? An article belongs to the poultry. You have assigned it to poultry. Okay, this is good. 1. An article is true wheat article, but you have assigned most of them to poultry. Okay, so is this a good confusion table, confusion matrix or not? Can anybody tell me? Is this Are these results good? Can somebody tell me how to interpret these results? Are they good results? What would be the perfect results for a confusion matrix? I told you what would be the perfect result for the contingency. I don't want to see any false negatives or false positives. Yes, all values in the diagonal should be non-zeros, okay? The rest of them should be zeros. So it looks like this, I have a problem here, okay? This class wheat is doing very bad because the true class is wheat, but I am assigning it to poultry. True class is wheat, but I am assigning it to UK, right? Also, I am having problem with the interest, and I am having problem with the trade, okay? Coffee and interest and coffee and trade being intermixed, confused. Okay, so that's why it is called confusion matrix. It's called confusion matrix. It is telling us what kind of confusions I am having between any classes. Okay, and if you like to do the recall precision and accuracy on the confusion matrix, okay, but recall and precision are done for each class. Fraction of documents in class I classified correctly. Okay, recall is that, and precision is fraction of documents assigned class I that are actually about class I. These are the new definitions for confusion matrices, and this is the accuracy, fraction of documents classified correctly. These are all fractions, and these are all between 0 and 1. Okay. Remember this one? This one said that recall true positives over true positives plus true false negatives. Okay. So this corresponds to the same thing in the 2x2 contingency matrix. 2x2 contingency matrix is a very special version of this one. Only this part. Okay, good. So these are some metrics for the confusion matrices, and sometimes people do this. Sometimes, since they have the class-wise performance of the confusion matrix, let's combine them together. How do I combine it? I sometimes combine it this way or sometimes that way. Macro averaging is you calculate the performance on each class. It is either accuracy or precision or recall. Then take the average. Or sometimes you do collect all decisions for all classes and compute the contingency table. Okay, something like that. Okay, so macro average in this case, macro average precision and macro average precision in this case 0.5 plus 0.9. 0.5 comes from here, okay, because 10 plus 10 over 20 is 0.5, okay, and this one is 90 over 100 is 0.9. This is 0.5, this is 0.9, over 2 is 0.7. But in this case, I add these numbers. I add this one and that one, this one, and that one. And I calculate my micro average table. Okay, So its number is a little bit different with the micro average. With the micro average, you don't do any calculations. You add them all and you make your calculations. With the macro average, you do your calculations and you take your averages. Okay, so with the micro average, precision, okay, if one of your classes is very dominant, it has many samples in it, then that's going to dominate everything else. So I'm not saying that one of them is better than the other one. Depending on the situation, you may use one of them. Okay, good. Once we have our precision, recall, F1 and accuracy numbers, okay, we can use them on our test set. But usually, when we are doing our development on our data set, this is how we split our data. Let's say I have 1,000 cases. Previously I said that it is 972 to 30. We don't do it that way, okay? We do it this way. For the training set, sometimes let's say we have 800. For the development set, let's say we have 100, and for the test set we have 100. Total is 1,000 now. So what is the difference between development test set and test set? Development test set is this. When we are doing the naive Bayes or any other machine learning technique, okay, sometimes we have to make decisions. For example, should I use the advanced smoothing or good string smoothing? Should I use the stop words or no stop words? If I am using the stop words, what kind of stop words should I use? I have to test these ideas, right? So I do all of my testing on the development test set. Okay, I train it, I change my parameters, and I look at my results in the development test set. Once I am satisfied with my classifier, I report my final numbers in the test set. Test set is not seen at all. You run your final result on the test set and you never touch it again. Because if you keep running your classifier on the test set, you are learning your test set now. You don't want to do that, okay? You don't want to do that. And when you are playing with your development test set, okay, you don't keep your development test set the same. You always change it, okay? This is called cross-validation, okay? This is your 800 samples. You use this 100 of them for this case, and 100 of them for this case, and 100 of them for this case, okay? So every time you make a new experiment and that kind of stuff, you keep changing your development test set so that you are not overfitting your machine learning model to your training set. Okay? As I said before, test set is only touched once or maybe twice, and that's it. Okay, good. So that's the evaluation part. And for the real world problems, some of the real world problems, okay, how am I gonna find the training data? I think I had a question about this. I mean, wheat or grain, wheat or bread, okay, should I categorize them as the same? How am I gonna do the stop words? How am I gonna classify them? Okay, these are very difficult to make a decision if I am doing the hand labeling, okay, manual written rules. So if I have some training data, maybe I can get more labeled data running some naive Bayes very early versions of maybe a early version or 0.1 version of your software first and get the results and ask the humans to say yes or no. Okay, so instead of asking humans to label your data, you may ask your volunteers or your paid markers to verify the results of your system. And of course, you don't do it with a single person, you do it with many persons to see how they are agreeing with each other. So getting the data is always problematic, and especially if you are working with people, such as sentiment analysis, etc. It is always problematic, and you don't want to get your results from a single person only. Okay, and if you have large enough data, then you may try the other classifiers too. Okay, so I will skip this one. With enough data, it looks like the systems in naive-Bayes or perceptron or memory-based, the memory-based, I think it is KNN type of stuff. They work very similarly. Okay, some of them are doing good with the small number of data. Some of them are doing good with the large number of data. But usually, more the data, better the machine learning system is going to behave. Okay. Good. I'll skip these. And I think we have the same suggestion when we do the n-grams. Since in our formulations, the formulations are always PCJ times PCJ times XI. Okay. If these are the formulations. Okay, so lots of p-value multiplications, and many of them are close to 0. If you keep multiplying them, you will end up having an underflow, and for underflow, our trick is using these logarithm. Okay, if you do these multiplications, xi, just take the logarithm of it, and at the end, do this. E to the power logarithm of this stuff. But with the logarithm of 2 multiplications, it is additions of them. Okay, so instead of doing the multiplication and taking the logarithm, take logarithm of each and add. Okay, and that will give you exactly the same result if you take the e to the power thing, but in terms of computer precisions, okay, you will not lose precision. You will not run into underflow problems. Underflow prevention, log space. Okay, instead of continuing with this, I like to give more information about the sentiment analysis. As I said before, sentiment analysis is something that we define as a specialization of text classification. That's why I like to look at this sentiment analysis in a more careful way. Okay, when you do for example, Google product search, okay, if you look at this one, people are writing lots of comments about that product, and they are assigning lots of stars or the scores for each product. These are very good data to do sentiment analysis because the data is already labeled. Okay, but they are not labeled in terms of the whole product. They are labeled in terms of value, setup, size, mode, and colors, and etc. Okay, so these are very important. This is very important. This is very valuable data, because using this data, I know how to interpret if somebody says something about my product. I know how to evaluate it, how to give stars to it. Okay, how to give stars to it. And similar stuff is used to classify the Twitter messages. Okay, this is, you know, this Gallup polling company, okay, or the organization, institution. They do polling about your products. They do polling about the economy. They do polling about the consumer confidence. And they spend lots of money to do this polling. They keep asking people, calling people, and they are asking their opinions about the economy and everything. Some people say that instead of looking at the Gallup data, maybe we can do the Twitter sentiment analysis. How the people are showing their emotions with their tweets. And it looks like the Gallup poll and the Twitter sentiment analysis, they are following each other. Okay, so with February 2009, stock market bottoms out and begins the recovery. So the Twitter sentiment is going up. Okay, well, in this case, when in 2008, one of the companies went bankrupt. When it went bankrupt, I have this downward trend both in the Gallup and the Twitter. Okay, so very important information from Twitter. What I'm saying is that sentiment analysis is very important. Sentiment analysis is important. Okay, so skip this one. I will skip this one, and I will try to go into why we are doing this sentiment analysis. Opinion extraction, opinion mining, sentiment mining, subjective analysis are the other terms for sentiment analysis. Okay, where we do the sentiment analysis for the movies, products, public sentiment is important. For example, the confidence, economic confidence, with the politics, which political party is going to lead in the elections, and etc. Okay, so for the sentiment analysis, we need to look at the human psychology. Okay, human psychology. How the humans think, how they behave, what kind of reactions they give to what kind of inputs. This is the study area of human psychology. Somebody named Scherer, okay, made a topology of affective states of humans. Okay, for the emotion category, you may classify the human emotions as angry, sad, joyful, fearful, etc. Okay, for the mood, I am in a cheerful, gloomy, irritable, listless mood, etc. Personal stances, attitudes, and personal traits are other categories of human affective states. Okay, affective states. For the sentiment analysis, attitude is the key category that we are dealing with. Okay, and this is the definition of the attitude. Okay, enduring, effectively colored belief. Okay, the position towards objects and persons. Okay, what a person believes towards an object, event, or person is our interest. Are they liking it? Are they hating it? Are they valuing it? And etc. Sometimes we can simplify this even further. Okay, we say that their attitude towards this person toward the president is positive or negative. Okay, so this is an affective state of human psychology, and each human, like it or not, will have this attitude towards objects and persons. Okay, each person has these kind of feelings, and we like to know them because attitudes are driving people behave in some ways. For example, if they have positive attitudes towards my product, most probably they will buy it, or they will suggest it to somebody to buy it. Okay, so with the sentiment analysis, we like to discover these attitudes. If you like to do a very detailed sentiment analysis, sentiment analysis, given a sentence, for example, I like this movie. I like this movie. This is a sentence. If I am doing the complete sentiment analysis, I like to find the holder of the attitude, who is saying this, target of the attitude, towards which target I am having this attitude, type of the attitude, like love, hate, value, desire, etc. And the text is already here. Okay, but we usually don't go this much into detail of the sentiment analysis. We ignore these two, and we usually come after this one. Okay, positive, negative, neutral, together with strength. I mean, very positive, very negative, positive or negative. Okay, so we are only just small part of this sentiment analysis. Okay, most of the time this will be good enough for us, but sometimes, I mean, you cannot. Is this a positive sentiment or negative sentiments? Is this a positive sentiment or negative?
Positive, of course.
When you say positive, of course, we are thinking in terms of, okay, your target is a movie, the holder is the user reviewer. How about this one? Is this a Armenia lost 3 villages? Is this a positive sentiment or negative sentiment?
It's like information, but it depends on who's reading it.
It depends on who's reading, or it depends who's writing it. Who is the holder? Who is the target? Okay. If you say somebody is saying Armenia lost 3 villages, if that person is an Azerbaijani person, okay, if the holder is Azerbaijani, if the target is the news, if the type, in that case the type of the attitude is positive, right? So usually the polarity depends on who is the holder and who is the target. Okay, and most of the time we will run into these kind of problems, but we are ignoring it, and usually we give this kind of stuff. Okay, simplest task is the attitude of this task. Okay, positive or negative. More complex is doing all of them, 1, 2, 3, 4, 5. Okay, and advanced is just simple task is positive, negative. More complex is positive, very positive, negative, very positive, and neutral. More advanced is the detect all of them, holder, target, and the type. Okay, and mostly the data sets that we have, they do this positive, negative thing. Okay, so usually it is not that easy to, let me show you some of the problems without going to that kind of problems. Let me show you the sentiment stuff. Yeah. In terms of thinking naive bias, okay, this is how we did the naive bias. And we are evaluating each word separately, but the problem with this is this. Okay. If you look at the first review here, this film should be brilliant. It sounds like a great plot. The actors are first grade. The supporting cast is good as well. And Stallone is attempting to deliver a good performance. However, it can't hold up. Do you think Naive Bayaz is going to do good or bad on this one? Because I am going to do this P given positive. What is the probability of this? Well, maybe this is irrelevant. Let's ignore that one. Okay. How about this one? Given positive, what is the probability of brilliant? Yeah, high. Given positive, what is the probability of great? High. Given positive, what is the probability of first grade? High. Good is high, but the movie is a negative. The review is a negative review. Okay. This is not a positive review. It's a negative. Okay. So naive Bayes kind of classifiers are going to have difficulty in these kind of reviews. Why? Because people usually they don't say whatever they mean to say in a direct way. They try to use these kind of sentences. And this is not an exception. This happens a lot. Usually they become ironic, they become sarcastic. Okay? They say one way but they mean the other way. Okay. Good, I guess that's it for today's lecture. If there are any questions, I can take your questions. I skipped lots of stuff. Maybe I will repeat some of them in my next lecture, but I don't know, but they are not that important. The important thing here is that I showed you the naive Bayes, and that was important. And I showed you how to evaluate our machine learning evaluation results. Okay, any questions? Okay, if there are no questions, that's it for today. Thank you.